Okay, good afternoon, good morning, good evening. So thank you very much for joining us today for the talk of Luciano Ost from Loughborough University in England. And the session chair today will be Professor Leandro Soares Indrusiak from University of York in England. And as I already told you, if you see the YouTube channel, there is also a very nice talk available there that was done last year by Professor Leandro Indrusiak. So now the floor is with Leandro to start the session with Luciano. Thank you
All
very
right.
much, Leandro, to accept to be the session chair today.
My pleasure, Ricardo. It was my pleasure to give a talk in this seminar series. It's my pleasure to introduce my colleague, my friend, my former student, Luciano, for this talk. In general, I would like to ask people to start preparing their questions and writing their questions in the chat. We are going to do the questions at the end, as it is the case in this seminar series. But you can already start writing them into the chat so that we can, at the end of the talk, read them and get Luciano to answer. So Luciano started his academic career long time ago in the city of Uruguaiana when I had my first lectureship, and he was one of my students. And from that point, I could track his career and see his progress from an undergraduate to a master to a PhD student with the Catholic University in Porto Alegre under the supervision of Fernando Moraes. I was happy to be a co-supervisor of his PhD. He spent 1 year with me when I was back in Darmstadt. And then after that, he got a position as a research assistant and then as assistant professor at the University Montpellier in France. And after that, he took a position at the University of Leicester here in the UK, and then moved to the School of Mechanical, Electrical and Manufacturing Engineering at Loughborough University, where he currently does his work as teaching, in research, in program leader of one of the degree programs in Loughborough. So Luciano is fairly busy, and I'm glad that he found the time to share his expertise with us. So, Luciano, the floor is yours, and we're listening.
Thank you very much, Leandro, for such kind of introduction. So, let's start. Good afternoon, everyone who is attending the session. It's my pleasure to share a little bit what I have been doing along with some colleagues from mainly from Federal University of Rio Grande do Sul, for example, Ricardo Reis, and a few students that I have been working with for a while already. So basically today I'm going to talk about some challenge or discuss about some challenge and needs related to the early embedded deep inference network software error assessment and mitigation. The idea of this talk, I'll basically describe the benefits of using virtual platforms as an efficient way or means to address and cover the presented challenge that I will discuss later on. My idea is to finally, or after that, I'm going to present you 2 case studies where I'm going to demonstrate the benefits of using virtual platforms and where I'll be able to demonstrate some prominent results that we have considering deep inference neural network software analysis and mitigation. So there is a vast number of machine learning algorithms, and those are being used or incorporated in several domains, systems, aiming to recognize pattern and to react efficiently to different and unexpected circumstances. So there are plenty of algorithms, and among of those algorithms, I can highlight, if the animation allows me, that deep learning is definitely among of the top, I would say, priorities of academics and industrial AI researchers. If you look at this slide here, there are few examples where deep learning has been demonstrated reasonable superior performance when compared to other network models. In some cases, those are even exceeding human occurrence, as already reported in the literature. Deploying such deep learning models on real-time embedded systems and edge device is a reality, and I might say that it's a reality that is becoming even more critical given the emerging challenge on those devices. So deep learning models, they are deployed through two main steps or two main phases as we wish, and which includes basically networking training and inference. The training phase could take hours or even days, depending on the amount of data that might be necessary to train the network. The network training, as we can imagine, it's performed offline, and that usually is done with some high-performance computer with some considerable computation power. Here I'm talking about machines with up to tera operations per second capacity. Once you train those networks, then we're supposed to optimize them, looking at or considering a specific target hardware or device. And those are used to either infer or predict some possible outputs, considering new data. The on-device inference networks, they require a much lower latency when compared to networks that are used during the training phase. Here I'm talking about milliseconds rather than hours or days that we can see during the training phase. And of course, this is a challenge when you are trying to port those to resource constraints kind of device. One example of technology that is using machine learning or set kind of machine learning algorithms is self-driving cars. Those they are expected to integrate deep neural network that might be just as complex as those found or that are used in high-performance computer or data centers. As I just said, porting complex algorithms takes time. We need to be able to not only to calibrate, but to check their precision when you optimize them to infer, to execute them in our target platform. When we are porting those kind of algorithms to systems such as this Tesla self-driving chip, this is something like is easier and more achievable when comparing to a research constraint kind of platform. Here we can see that we have inside few TPUs units, we have the embedded GPUs, we have a specific image processor plus 12 ARM A72 CPUs, which are devoted to execute complex software stack. Software stack is operating systems, drivers, and definitely machine learning algorithms plus few applications. However, most of those machine learning algorithms, they do demand, as I just said before, a high or considerable computation power to perform massive and complicated calculations, if you stop and think, which somehow restricts their execution on time and resource constraint kind of device. Even though some, let's say, customized or bespoke neural network has been investigated in the market, we still have a place to go. Aiming to enable the execution of those, let's say, tiny or bespoke, optimized kind of networks, few researchers, industrial researchers, and also academic research, they have invested on some kinds of libraries, APIs, that we can use to deploy some deep network on different processor architecture. Here, for example, I can present to you few of those libraries. Here I mean, for example, the STM, Cube AI, CMCs and N, CMIX and N, and also TensorFlow Little. So those, we can rely on those APIs or libraries to set some functionalities and to parameterize the kernel of a neural network, aiming to support their execution on device that do rely on a lower performance or computation and memory capabilities. So far, people have investigated, or they have proposed, they are investigating new APIs and libraries, and at the same time they are evaluating which are the benefits that they can get when they do so. So basically they are considering the achieved performance, and they are comparing how accurate they still can be when they are able to reduce, for example, the memory footprint. And if you go to different papers in the literature, you can see that people are doing that. For example, this is the CMIX and library that has been proposed by Benini's group. And they have used this basically to allow, with this library, they enabled us to play a little bit with some parameters, aiming to facilitate or to enable us to minimize or to play with precision and memory requirements, for instance. We have in-house, developed in-house, I have some students who are playing with those libraries, and we can see that depending on how you set your network, we can then gather better results in terms of execution, or you can reduce a bit the amount of memory that you can play with. So here in this example, basically we took the mobile net image, the ImageNet mobile net network and data set, and we have executed that on the top of a Cortex M7 library processor, sorry. And we have disabled here the cache, and we have played with different APIs and libraries such as TensorFlow Little, CMIX and N, and so on and so forth. And we have done that considering other microcontrollers as well, using different boards. But this is, you are just playing a little bit to check how can you optimize them, and with kind of trade-off we'll be able to do, not only considering their performance and occurrence, but also their reliability. And that's what I'm going to discuss more in depth later on. So we do know that the resulting scenario, so we are dealing nowadays with complex software stacks. We are running those complex software stacks on the top of single or multi-core processors, which are operating in aggressive clock rate, at aggressive clock rates, and we can consider in some system multiple voltage domains as well. We do know that on surface on Earth, humans and electronic computing systems are exposed to radiation from different sources. I can mention, I don't know, cosmic and terrestrial kind of source. Radiations, for example, emitted by rocks. And we do know that. While such kinds of, such types of radiation, they do not significant effect or has some health hazard to humans, they may affect the operation of electronic computing systems. And the occurrence of those errors, they may lead, for example, to if you take as an example a self-driving car or a medical device, or they can put humans' life at risk. And our idea is always try to reduce the probability of that to happen. So here I bring the first question that I'm willing to answer to all of you. So how can we assess the software reliability of today's and emerging electronic computing systems? So there are plenty of challenges there, and to answer such question, I believe we should take into account at least 4 of challenges that I have, at least that I consider as the most important ones. So firstly, we must provide software engineers with efficient way to enable them to appropriate or to conduct large numbers of fault injection campaigns within a reasonable time, and mainly early in the design phase. Secondly, I believe we must provide them with some kind of observability, because you must be able to check the system behavior when we expose them to the occurrence of an error. How does my software stack would react? How my operating system would see that flipped bit, for example? Would that lead to a fail, to an error, to a crash? So we must have some kind of observability to check that in a good way. We also must be able to identify the relations and associations between application profile and our target platform. And we must also be able to consider a large data set, because you must be able to run a lot of fault injection campaigns and aiming to collect a considerable amount of data that will allow us to build some conclusions or more accurate conclusions on the top of that. And finally, we definitely must be able to investigate new and efficient mitigation techniques aiming to tackle the occurrence of software errors, considering complex software stacks. So which approach should we use? So currently, there are common approaches to assess the software error reliability that considers the use of either ASIC or FPGA boards. We can either here consider the emulation, or we can port our system to one of those boards and expose them to radiation. This kind of approach has some limitations. They are costly, they have some limit in terms of resource, and a lower kind of debuggability and observability, I would say. For example, we can take this as example. When we are evaluating a single core running there, is somehow easier try to identify from where an error comes from. But let's take a more complicated kind of system where you have multiple single cores that do exchange messages through a network on chip. You'd be somehow, that adds some complexity on how to observe from where the error might comes from, mainly when you expose this kind of systems to radiation. We can also rely, or another approach, consider the use of a lower level kind of simulation. So here I'm talking about either register or gate level approach. Here we have more observability, definitely. However, it demands a huge amount of memory to simulate some simple kind of systems. And also, this kind of approach is not very applicable to large scale system, and the main limitation at my point of view is the lack of, for example, processor descriptions that can be available, for example, to universities to conduct some research on the research on the top of that, or considering those open kind of processor descriptions. Now we have RISC-V that is that can help us a bit, but still that's just one single source. The use of system C can boost up a bit or reduce a bit the overhead inherent to the high simulation cost. For example, to run a simple deep inference network, here I'm talking about CMCs and N on CFAR10. A single execution of that on the top of a Cortex M3 processor in RTL takes from 3 up to 4 hours, a single execution. And as you know, we must be able to run few fault injections there. So how to overcome that? My opinion, my proposal, and few other researchers, they have been looking at that, is the use of virtual platforms, which I believe is a prominent kind of technology that can provide us with some facilities. The main idea of virtual platform is the fact that you can execute the same application, the same binary that you are later on to execute on the hardware. On the top, you can execute the same code on the top of virtual platform. You can expect the same result. Here, just an example of a kind of system that you can model, CPU, memory, and WART drivers and things like that, and you can somehow mimic the simulation of a real code. We can consider real compilers and run that at the same way that you would execute that code on the top of a board. There are few kind of virtual platforms. They do differ in terms of occurrence and simulation performance, as you can expect. So here, another question. Under what conditions do virtual platforms can overcome the underlying limitations? And here I have just some comparison where I do believe that virtual platforms can somehow overcome certain limitations when compared to the most common or current approach related to the software error assessment. So here is the principle. There are some solutions which have been proposed in the literature, but my principle, or the principle that the people, the researchers that I have been working with, is the fact that we don't want to eliminate the common approach adopted in literature, but rather we are investigating a more, let's say, prominent or effective way to eliminate not suitable solutions, and then take the best candidate or 2 or 3 best candidates and then go straight down to the final goal. That would be to expose that to radiation, and then check whether the new techniques or the mitigation techniques, or whether that software stack configuration or processor would provide us with the necessary trade-off between performance and reliability, for example. So if you look at the literature, there are few works that have been used virtual platforms to tackle, or to at least to boost the design space exploration of considering the software error reliability analysis. So if you look at the literature, so apart from our framework that I'm going to briefly present to you in the next slides, we are basically, we can say that we are the only, or that we have in-house the only framework that considers not only the software assessment, but also an automatic application of mitigation techniques. And all of that is integrated in one single framework, differently from what we have seen in the literature. So the produced framework is called SOPHIA, and that's a cross-layer investigation tool that somehow covers the challenge that I have mentioned before. So we have defined this in 3 main. Our solution target those challenges in 3 main groups. So we do have support for profiling and software error assessment, some automatic kind of software error analysis, and automatic mitigation application. SOPHIA employs 2 fault injection or 2 virtual platforms that were extended to support the fault injection kind of activity. And I'm talking here about GEM5 and OVPSync. So aiming to tackle the challenge 1, 2, and 3, we have proposed not only an infrastructure that enables to inject faults, to classify them, but we also have enhanced it with some simulation performance techniques that enable us to conduct large-scale kind of fault injection campaigns. Here, we talk about simple and well-known checking points, but also we have implemented this tool set in a way that you can port that, and we can run up to thousands of simulations in parallel when considering, for example, high performance computing. This has been built considering well-known distributed tool set, so that allow us to use different or the most common supercomputer facilities. We have already used that in 2 supercomputers here in the UK, and it works. So having aforementioned performance capability is essential to deal with emergent and complex software stack, such as those found in the automotive industry. Some studies are pointing out, or they are predicting, that up to 60% of a car will be software. And to deal with such kind of complexity, we need to find ways that would enable us to verify the software assessment within a reasonable time. Just to give you one example that we have done in-house, let's take this automotive case study as example here. So I'm talking about this visual odometry application, and we have executed them just to show you how different can be the simulation performance when executing that on the top of a GEM5, for example, virtual platform, when compared to OVPSync. Here, I'm considering single, let's say the average run of a few, the average run of this application, considering some variations here. So this more or less is the average time to execute this application one single time. So would be unfeasible to conduct the software evaluation assessment here using GEM5, for example. Can you imagine trying to do that using at RTL level? Impossible, let's say. It's possible, but unfeasible. So we have considering this experimental setup just to check whether the injection of fault would generate some errors. And as we can see here, that the occurrence of fault or bit flips on that application lead to some wrong position of the vehicle. So the vehicle, in the end of that, has stopped few meters from the expected right position. So here I'm going to present you the first case that I have prepared to you, where I'm going to check or try to answer that, is there any kind of relationship between the software errors and the model occurrence when you are looking to deep inference kind of network? It's important to mention that in that case, in that automotive scenario here, we are considering a convolutional neural network case. And here, for this case, the same. So if we look at the literature, few researchers, they have looked, or they have made the software assessment consider different machine learning kind of algorithms. Some of those, they have exposed FPGAs to radiation. Others, they have target GPUs, scenarios. And here we are looking at research constraint kind of systems device. So we are looking to microcontrollers based device here. So here, then I believe I'm calling this as a contribution because as far as I know, we are the first to check or to analyze the impact of the precision bandwidth on the software error reliability of the ImageNet MobileNet network. So as I mentioned at the beginning, so there are few libraries and APIs that we can use to somehow to tune our network, aiming to enable its execution on any device. So this is the library proposed by Benini's group, and basically here in this example we have played with aids and input data bit width, aiming to check their impact on the software error reliability. In order to estimate more or less the percentage of error from the MobileNet case study, this table shows more or less the experimental setup that we have used to run this case study. We can see here that we have considered different cases. For example, we have conducted fault injection campaigns injecting files only on those layers here individually here, but also consider the entire execution of our deep neural network. Aiming to evaluate the software reliability, we have then assumed or we have adopted the shows fault injection fault classification that consider 5 main groups: vanish, application, output, not effect, and so on and so forth. But we considered this classification, and on the top of that, we built up our own classification. Why? Because you want to see which of those errors would actually lead to either an incorrect probability or wrong or misprediction. Yet again, I haven't mentioned it. We are considering here a convolutional neural network that classifies an image according to 10 groups that basically gonna set whether it's a animal, it's a cat, or it's a car, and things like that. So observing here the effect of quantizations on the CNN reliability, we can see that the number of OMM increased from 5% to 35% when you increase the bit width for W and for the input and output data here. Something that's also important to highlight is that the high occurrence of ONA and OMM in different separate convolution networks. So we can see that that differs from one layer to another. Why that's important? Because we must be able to observe which of those layers are more suitable to the occurrence of software error. So then we might decide later on which of those layers we can then try to protect, for example. Here is the most important, I believe, outcome from this experiment here, that we can clearly see that in this specific configuration here, we can, on those two configurations, when you play, we have a higher precision, I would say, you can see that the numbers of critical and tolerable errors, they do increase. So we can clearly see that in this specific configuration, when we inject the files in the entire network execution, that up to 12% of those errors, they are considered critical here. That means they would lead to a wrong classification or to a percentage reduction when classifying a given image. So here's some conclusions here in this specific aspect. It shows that that the evaluated result, they somehow show that the higher precision bandwidth configuration present higher susceptibility to the occurrence of software errors. Low precision bandwidth configuration increase the masking rate by up to 21%. Moving forward, because I'm needed to use the second case to tackle the challenge 4. That is something that I haven't discussed yet. So how can you reduce the occurrence of software errors in the inference network? And this is what I'm going to try to answer. Which kind of techniques should we use? So replication approach would be suitable for such kind of applications. Remember, we need to optimize them to enable their execution in edge device. So I mean device with lower memory footprint, low memory footprint, and some reduced computation capabilities. And here for this example, we are considering the CMC CNN on CFAR 10. Someone can claim or can ask, okay, Luciano, the majority of machine learning models or algorithms that are employed in embedded systems, they rely on CNN kind of network. And those networks, by nature, they do present a lot of redundancy there. So that basically they are built in. So at some point, somehow, they are somehow tolerable to the occurrence of software errors. But yet, I do believe that we still must investigate and try to avoid at most the occurrence or the possible occurrence of critical errors in any kind of system. Remember, we can have some of those deep inference kind of networks running in medical device, and an error there can be crucial. So looking at that, we have proposed a new technique, a lightweight technique that relies, that has been built on the top of Silang LLVM compiler, on the back end of the LLVM compiler. So basically, this joins one of our assumptions as well. We do believe that the entire replication of code might not be suitable for any kind of device, because the complexity of those is constantly increasing. And we do believe that we can, at some point, to look at which parts of our code we can look at, for example, of the layer, or which are the critical function of a given application, and then let's try to protect that part. So based on departing from there, so we have built the RET. So what RET does, RET somehow extract the essential information in terms of the processor register utilization, considering the critical function of our application. And then you can play with the object code. We can try to restrict on which of those registers you be used to execute that critical function. And basically, aiming to support that execution, we just add some move instructions before and after that specific code. Just to exemplify, applications, they are built based on different functions and layers here. And let's consider, for this example here, for the sake of simplicity, let's assume that layer 1 and layer 2, they have the same execution time, and that the fully connected layer here somehow utilize the entire register, the general register available to our target processor here. So what it does, we had somehow taking an outcome for a profiling phase that I haven't mentioned before, because you run other applications, you do the profiling, you check the register utilization, and based on that, we can then set and tell to RAT to protect those, or in fact, to restrict where that layer, for example, will be executed. So in this case, we would restrict the execution of that critical application there, then reduce the probability of a bit flip that would reach one of those layers to lead to a possible error. So basically, the proportion of time, of course, because this would add some overhead, but we'll be able to see in the results later on that it's valuable to, or reasonable to have that overhead, given the improvement that we can achieve by using RAT. So what else is important to say here? That the proportion of time that we have that layer execution is somehow equally to the probability of a random fault to achieve, to reach one of those registers here. So looking at the experiment that we have, we can see that when we apply replication kind of approach, here I'm talking about TMR and partial TMR. The partial TMR here considers the protection or the replication of our critical function only. Okay. In this case, the multiplication within the convolutional layer here. So the inefficient of the TMR versions here is mainly due to the hardening approach applied to the LLVM here, that basically use the majority of the available registers in the system. And this also leads to a lot of extra memory operation. And as we know, memory operation, they are slower than register kind of operation. So here we can clearly see the benefit of using RAT. We can see that its overhead in terms of execution time is near to 11% extra when compared to its the normal execution of CMC's CNN on CFAR10. And we can also check that the number of critical and tolerable errors is reduced. Here we can look more clear, taking into account the mean working to fail, that we had reduced the occurrence of critical errors by 3.4 times. So these are considerable reduction when you can give it's a considerable reduction taking into account the extra overhead. Infected overhead of is 27%. At some point in time, to finalize, we can see that RAT might not be very efficient, because the idea is to be able to explore many variations, like to restrict which registers we are going to use. And in order to do that, we must have like some efficient and faster kind of approach. That is the one that we have proposed here, that would allow us to explore or to run this large kind of design space exploration, aiming to reach the best balance or trade-off between performance, memory utilization, and reliability. But still, our technique might not be efficient enough. So our next step is to look to a hybrid kind of solution. Here, one limitation, for example, here we are just looking at the register file of the processor. So what about memory? So considering here the MobileNet ImageNet case study, we have injected also fault injections on memory. And we can clearly see that the flash and memory, that faults injected on the flash and then on the RAM, they do have a considerable high effect in those kind of application. This is not applicable to every kind of application. We have run similar experiments considering applications from other domains, but particularly deep inference networks, they do present such kind of behavior. For that reason, it's important to take into account the impact of injecting faults in the memory. And we are looking at that at the moment. Of course, that one of our next steps as well is try to validate rat by exposing it to radiation. It's be more difficult to find some conclusion out of there because an error can or a particle can read any part of the board, and it'll be difficult to check whether you're going to read exactly the register of our processor, but we're gonna give the try. Aiming to show the benefits or to prove that RAT works, we are also conducting some investigations considering lower level fault injection approach. I mean, we are using like emulation using the board. So we are conducting this in collaboration with Grenoble University in France, where we are using some GDB kind of fault injection approach. So we'll be able to check exactly which would be the impact of protecting our machine learning kind of algorithms using the RAT technique. I can anticipate that we have already some results, and the results are kind of prominent, and they somehow prove that the mismatch between our fault injection approach using virtual platforms when comparing to GDB is below than 5%. That's quite useful. So here some related publications that somehow summarize part of the results that I have discussed here. And I'd like to thank all the people and students who are involved or had contributed considerably to this for all those results here. Thank you very much.
So thank you very much, Luciano, for this talk and for giving us an overview on the difficulties of testing systems with regard to soft errors, and also how to make them more resilient to that kind of that kind of problem. At the moment, I'm looking for the chat box here, and I don't see it. I think Ricardo will make it available for me soon. Before that happens, I would like to start with the questions. And the first question that I have is related to the application domain. As you mentioned, a lot of the computer intelligence applications, such as neural networks and machine learning, they have a lot of redundancy embedded in them already, which makes them perhaps not the most immediate candidate for your techniques. So my first question is, why did you pick this particular kind of application? And what are other kinds of application that perhaps don't have that embedded, included redundancy, and perhaps could benefit a lot from your techniques as well?
Thank you for this very interesting question, Leandro. And definitely we have considered other or applications from different domains. We have results. We have applied a RAT, for example, considering tiny kind of embedded applications. Let's take, for example, from different benchmarks, and the results show us that they do benefit way more than machine learning kind of applications. I'm considering answering the first question now. We have considered those machine learning kind of applications because they will be employed, for example, in some systems to control, for example, drones. They are looked to the adoption of machine learning algorithms, aiming to automate their their movement from A to B, considering not a single drone but multiple drones running in parallel. And people are taking machine learning to somehow they are basing their control, their navigation control, using such kinds on application. And I do believe that although the number of critical errors is definitely lower when compared to other kind or applications from other domains, an error there might be more critical, or might lead to something more critical than other fields.
All right, yeah, that makes sense, and that also pushes for a more cooperative approach between what you do and what people, for instance, from the control community, they do, and they try to get robust control algorithms in the real-time systems area. The people that deal with real-time control, they try to handle the problem that occasionally you cannot really read from the sensors, or every now and then there will be some problem that you have to apply your control algorithm with stale data that is from a few cycles before, because you couldn't really get an accurate reading of a sensor. So putting this in context, that there are many kinds of problems that a particular control algorithm has to deal with. They could be related to soft errors, they could be related to other kinds of errors, and the control algorithm can cope with that, but not so much. And there is some interesting research from Martina Maggio that actually looks into this and evaluates how many problems can a control algorithm cope with, the point of view from timing failures. But soft errors would be an interesting point to look at as well. I haven't seen any. I found the chat now, but I haven't seen any questions there. So maybe I should ask another one, and people should be less shy and ask questions, and try to put Luciano against the wall there and get some tough questions for him. My next question is related to an area that I don't know very well and I don't understand very much, which is neural networks. And you've mentioned that you could actually analyze at which layer of the neural network you can have a particular error rate, and then have error rates that are different over the different layers of the neural network. And then based on that information, you can then try to use mitigating approaches that are different at each layer of the neural network. So my question, and coming from somebody that doesn't really understand a lot about neural networks, is why would the error rate be different across these different layers of the neural network? What are the aspects of the different layers that will make them more or less susceptible to soft errors?
So far, we are looking at that. Some of the reasons, or let's say hypotheses that we have, are one, the kind of instructions which are generated there, and how the execution of things, they may overlap, or they somehow they can rewrite the values in the register. For example, you can somehow the lower you go, the more the masking you can see, and you can see this masking behavior. That means you can have a bit that is flipped in some regions of the neural network, but due to the amount of operations that are handled there, this happens more often depending on the layer that you are. For example, when you look at the convolutional kind of layer, we can see that we have two main functions here that are basically matrix multiplications. And over there, easily, if a bit is flipped, somehow it doesn't lead to an error later on, because you're gonna override that value before propagating through the entire or to the propagating through the operation or the execution of the neural network. So this is something that we have already observed on our results.
All right.
Yes, because for example, depending on the layer, some of the neural networks or those libraries, they do rely on some kind of specific instructions, which are specifically to execute some parts of those neural networks. In some cases, in more, let's say, sophisticated kind of specialized hardware processors, such as the Cortex M 55 from ARM. So we can see that more clear because we have like a specific TPU-like kind of hardware that are devoted to execute that specific part of the application. So we can see that depending on the kind of instruction that execute, that can lead to more or less errors.
All right, it makes sense.
Yes.
Since we don't have any further questions, I will look into the chat once more. I think I'll pass. First, I would like to thank Luciano again for the talk and for the end, and thank everybody from attending. Thank you very much, and that's it.